thank you everyone for coming. Thank you to everyone online too. So today I'm going to talk about my work during my first year as a PhD student. So the name of the study is Comparison of Two Force Identification Methods from Full Field Measurement Performed with Optical Deflectometry. I have been supervised by Alain Berry at Université de Sherbrooke and by Quentin Leclerc and Kerem Ege at l'Institut National des Sciences Appliquées in Lyon, INSA de Lyon. So the objective of the study are to identify a force applied on the panel with two methods, two different methods that we will present on this seminar using optical deflectometry measurements. The second goal of the study is the comparison of both techniques that will be used in this seminar. So, to give you some context, measurements of the vibration field are made with optical deflectometry, and we inject those measurements in two techniques. So, the first one is the force analysis technique, or FAT, and the second one is the virtual field method, or VFM. With both methods, we get an identified forces, which should correspond to the one that we inject, and we can compare the results that, that we get with both methods. So that's what we are going to do during this presentation. Our work hypothesis, we are working on a homogeneous isotropic thin plate, which is submit to a transverse harmonic loading. So basically, it's a plate we work in pure bending. So without transition, let's start by presenting FAT, force analysis technique. So this technique is based on the strong form of the local equilibrium, and which is we call on the screen. We have a lot of terms, so let's take them one by one. First, we have the known and measured data. So the out of plane displacement W, structural parameters like the bending rigidity and the density, and geometrical parameter and the angular frequency. The unknown data is the pressure field Q that we want to measure with this technique. And to do so, FAT estimate the fourth order derivative operator, underlined in yellow, with a finite difference scheme. So let's imagine that you have a measurement mesh like the one shown on the screen. So you know the data are all the black points shown on the screen, and you want to estimate the pressure applied on the plate at the yellow point, which is here in the center of the plate. What we do is that we discretized this operator and use the 13 points, surrounding our yellow point in order to estimate the fourth order's derivative. So this is just simple math, but the main problem is that there is an amplification of the measurement noise because of this calculus. Since the noise that is already present in the data is mostly present in high wave number domain, you need to use a low pass wave number filter before calculating this operator. So we'll talk about how this low pass wave number filter is applied in our case. The second method is the virtual field method, and the main equation in this case is the principle of virtual work. So it is now shown on the screen, and there is still a lot of terms. So as we did with FAT, let's take them one by one. So there is still the known and measured data. We can find once again the out of plane displacement, and okay, sorry. Qu'est-ce que j'ai fait? Okay, sorry about that. So the out of plane displacement. There is also the bending curvatures, which has derived from the out of plane displacement. So it's just second order spatial derivative. Then we have some structural parameters. The density, Young modulus, and Poisson ratio will help us to estimate the elastic matrix of the plate, Q in capital. And then we have geometrical parameters, so the thickness of the plate, and an angular frequency. Concerning the unknown data, once again, it's the pressure Q that we want to estimate. And you might notice that there is some blue quantities here, which are... Mais je sais pas pourquoi je fais ça. Sorry. Which are the virtual fields. So basically, the virtual fields method is about choosing some functions who are called virtual fields and use them in order to solve the principle of virtual work, in our case, to estimate the pressure. So you have the virtual displacement, WV, and the related curvatures, virtual curvature, KV, that we derived from this virtual displacement. So in our case, you need to know two cases inside about our virtual fields. First, as I said, those virtual fields can be functions that are defined all over the structure, but in our case, we use piecewise virtual fields. It means that those functions, the virtual fields, are only known at some point of a virtual mesh. Plus, the second consideration is that we define this virtual mesh only over a small rectangular window, which is drawn on this figure. So you have the surface of the plate, S, and on the surface of the plate, you have a smaller rectangular window, SV. Then, our virtual field, virtual displacement here, are based on the Hermite 16 interpolation functions. So those functions are drawn on the screen once again. All you have to know is that we use those functions defined over a small rectangular window. We inject that in the principle of virtual work in order to find on pressure. So concretely, how we do that? Well, here's our virtual window position on our measurement mesh on the plate. Sorry. So as we can see, the virtual window is smaller than the entire surface. What we do is that we resolve the principle of virtual work over the small red area corresponding to the virtual window, and we identify a force applied at the center of this window. We might just identify the force as a pressure applied all over the window, but in our case, we made the choice to integrate this pressure and to only retain a small force applied at the center of the window. Once this is done, we move our virtual window to a next position. We do the same thing. We move it again, and like that, we scan on all the plate, and for each position of the window, we get a force applied at the center of the window. And that's how we estimate the force applied on our plate with the virtual field method. So we have presented FAT and VFM. Maybe an interesting point that should be noted is that VFM requires only second order spatial derivative of the displacement, while FAT requires fourth order derivative of W. This means that we already guess that FAT will be much more sensitive to measurement noise compared to the VFM. Okay, so now let's move on with optical deflectometry, which is the measurement used in our study to get the displacement field and the curvature field. So optical deflectometry is a full field measurement techniques. This means that with this technique, we can get at one instant a large number of measurement points. While with some other technique, you have to get point by point the vibration field. With optical deflectometry, we can get a large number of points. Plus, this technique is not measuring the displacement, but the local slopes of the displacement. So basically, the spatial gradient of the displacement. So let's have a look of how we do that. So we use a plate which has a surface treated like a mirror. And in front of this plate, we place a grid and we place also a high-speed camera. So basically what is happening is that with the high-speed camera, we can watch the reflection of the grid on the surface of the plate, which act like a mirror. So at point when the camera is recording the images, at point M of the plate, we can watch the reflection of point O of the grid. And basically, what the camera is recording will look like the little skin that you have at the bottom of the figure. So it's basically the reflection of the grid watched as the surface of the plate. So now let's apply a dynamic load on our plate. So a load Q is applied and a local slope will appear at point M. So now what the camera is observing at point M will be the reflection of point P instead of point O as we did later. And we will record some images look like that, and it's basically still the reflection of the grid, but distorted by the out-of-plane displacement created by the load. So now we have some record images when the load is applied, and how do we get the local slopes from there? We use this formula which link the local slopes, oops, sorry, I went too far, to some geometrical parameter. So the distance between the grid and the plate and the grid pitch also. But there is a third term, delta phi, which is basically the difference between a reference image taken with the camera when no load was applied and the deformed image taken with the camera when the load was applied. So basically, in delta phi, you have the information that correspond to the difference between those both images. And of course, we know the local slopes. So starting from there, what we do is that we get the record images. In our case, we had about 18,000 of images. We take a reference image which were taken just before the recording, and we put them into an algorithm, a black box, which allows us to extract term delta phi, which means that we can apply the formula that we saw and then find the local slopes. So for each recorded images, we get the slope fields all over the plate. Starting from there, we can, by numerical derivation, get the bending curvatures. And by an operation of inverse gradient, we can estimate the height of plane displacement, sorry. Plus, what is interesting in this WDFT algorithm is that a low-pass wave-number filter is applied to extract the data from the images, which means that we already somehow have a filter applied, which means that we don't have to apply an extra filter in order to apply the force analysis technique. Now, let's have a look about our experimental setup in a study. Here you can find the plate. You can see that indeed it has a surface which acts like a mirror. Our plate was made of aluminum and had simply support boundary conditions. The grid is placed in front of the plate, and you can see also the high-speed camera lens. So in our case, our high-speed camera was the Photon SX2, and it had a frame rate of 12,000 FPS. The shaker that we used to inject the force in our plate had a broadband input, which was filtered over 5 different octave bands. The force sensor was mounted on the shaker in order to measure the injected forces on the plate. So now, how can we get, how can we see if the force is well located with the method? Well, we have seen that we can estimate the outer plane displacement and the basic curvatures in the time domain. Starting from there, we can perform a time Fourier transform, which allows us to apply VFM and FAT in the frequency domain. So for each frequency that we consider, we get a complex cartography of the identified forces. What we do then is that we made an average map of all those maps, and we take the moduli in order to see if the force is well located. So here are the results that we get with VFM and FAT. So on the left figures, you get the force identified with VFM. So we can see that the black point is corresponding to the force, to the location where the force was applied. It is well located, as well with FAT. So both methods allow us to locate the method. And then we can use the signal that we get from the force sensor to see if the prediction of FAT and VFM in terms of force spectra are correspond with the signal that we have with the force sensor. So that's basically what we do in the second and last figure. In dash black, you have the force spectra identified with FAT. In green, the results for the VFM, and in red, you have the results from the direct measurements. We can see that there is some disagreement between FAT and the direct measurement in low frequency, but in the majority of the frequency that we consider, the force is well quantified. So finally, we have applied FAT and VFM to identify the load applied on an aluminum plate, and the measurements were performed by optical deflectometry. We have seen that we can well locate and quantify the load applied. If we have a look of the function that we use, we can see that FAT is quite simple to apply. And it has a local aspect, which is really interesting, meaning that when we apply the function, the technique, you don't have to know what is happening outside the 13 point considered to estimate the fourth order derivative operator. But technique is really sensitive to noise measurement and need some regularization. On the other hand, VFM requires less regularization, but the choice of virtual fields can bring some issue if you make a wrong choice. Some future work that can be done is to compare both methods, but in the identification of bending rigidity and structural loss factor on complex panel. And the application of FAT can be done using the slope field instead of the displacement field. When you apply the fourth order derivative operator, you use the displacement field. But if you consider using the slope field, it will require one derivation order less than what we do actually. So the noise will be less amplified, which can be interesting. So yeah, that's it. Thank you.